So the daily problem is max points on a line. The description's pretty simple, but you can pause to read it. But the gist of it is that we have all these points lying on a plane. We want to find the line that goes through the most points and return the number of points. Something we can immediately see is that there's only going to be 300 points maximum. So we don't really have to optimize all that well. We're not trying to get O of log n or anything crazy. And in fact, the brute force approach does just straight up work, which would be I would imagine O of n cubed. You iterate through every point and you say, for a given point, go through every other point and draw a line. Now we have a line, we have an mx plus b that we can compare things to. Compare every other point to that line and see if it lies on that line. And then just see which line has the most points. And I think that's about the lowest space complexity you can get, because that's O of 1 space complexity. You just have 3 pointers pretty much. And you have to keep track of the number of points on a given line. But we can do better. We can sacrifice a little bit of space complexity to optimize our time complexity. So instead what we can do is we can iterate through each point. And then once we're at this point, we actually don't really need the plus b of the mx plus b equation, because we know that we're always going through the same point. So any other point, let's take point 1, 1 here. Any other point that has a given slope that goes through this point is going to be part of the same line. So if we have 2 points, for example, these two, they draw the same slope to this point. So they're going to be on the same line as each other. We don't need to check as extensively. What we do need to do is just keep track of the number of points that have the same slope. So what that's going to look like is a dictionary, where we're going to say, add this slope to the dictionary, which is vertical, which is a corner case. And then now we have 2 points that have this slope. Add this slope to the dictionary, that's 2. Add this slope to the dictionary, that's 2. And then we'd say, oh, well, look at that. This point and this point form a slope that's already in the dictionary. So just add 1 to that. And then that goes from 2 to 3. And then we would do the same thing here, and we would find that all 4 of these points have the same slope with regard to any single one of these points. So that's what we'll do. We'll start out and say n equals length points. And then just have it's going to look something like for I in range points. What am I doing? I in range n. For j in range n. Except we can actually already optimize and say, we know this is going to be I plus 1 and n, because we don't really want to compare just the exact same 2 points that we've already compared. And then we're going to have something like x1, y1 equal, is that the order? Yeah, x and y equals points at I at 0, points at I at 1. And then we're just going to have the exact same thing, but for x2 and y2. So now we have these 2 points, and in fact, we don't need to recalculate this for every iteration of j. We can have this here. And now we can create the slope. So we'll say something like slope equals, what did I do? Slope equals y1 minus y2 over x1 minus x2. And you could have this be y2 minus y1 over x2 minus x1, or you could even have it be x1 minus x2 over y1 minus y2, or x2 minus x1 over blah, blah, blah. And it wouldn't really, none of that would really matter. That's just sort of looking at this from a different perspective. But what does matter is what's in the denominator. We do need to pay attention to that at least. If we had y1 minus y2 in the denominator, we'd be looking at that. But what's important here is we don't want to divide by 0. That would throw an error. And a situation where we divide by 0 is a situation where x1 is equal to x2. So like this line. When we're forming this line, y equals mx plus b doesn't help us, because y could just be anything, and x will always be 1. And that function doesn't really work. So we need a way to represent vertical slopes. So this is going to be some sort of if-else statement. So let's have this be the else. And then we'll say if x1 equals x2. So then here we're going to put, we could put, infinite, or we could put anything. We could put vertical. Or if you really wanted to optimize, you could put none, because that would take up slightly less space. But we'll put infinite because I feel like that's somewhat makes sense. It's somewhat readable to say that the slope is infinity. It's arguably it's not, because something divided by 0 is not infinity. It's indeterminate. But if you think about it, as the slope approaches infinity, the line that would make would approach this line. So it feels like a pretty apt way to call it. But it doesn't really matter, because ultimately this is just going to be a key in a dictionary. Let's define that dictionary here. So we're going to have something like slopes, let's call it. And what this is going to represent is the key is going to be a given slope going through point I, and the value is going to be the number of points that have that slope when you form a line with point I, which is what this slope is. So we just plug this slope into the dictionary. If we start out really simple, we could say if slope in slopes, slopes at slope plus equals 1, or else slopes at slope equals 2. Because any line we're forming will always have at least 2 points. That's kind of the baseline. And then we just have something like ans equals max ans and slopes at slope. And then we return ans. And finally, we have to actually initialize ans in the beginning. And I'm going to define it to be 1. The reason for that is specifically the situation, it will always be overwritten with at least 2. But specifically the situation where we have 1 point is the only situation where the answer is going to be 1. And so that's why we initialize this to 1. And the only situation where this doesn't change answer to be higher than that is this will iterate through. We'll find our only singular point, and then it'll say for j in range I plus 1 and n, but this will be in range 1, 1. So this will just skip over completely, and then we'll just return 1, which is what we want. So if we run this, it works, and it's actually about as fast as you can get. There are some theoretical optimizations that we can make, and I'll run through those, but as far as the solution, I mean, this is pretty much it. You could say none here, and another thing you could do that would be just unequivocally better is you could say slopes at slope equals slopes dot get, which is the same thing as this. When you say slopes dot get x, it's basically the same as this, but you can also specify a default. So if slope isn't in slopes, then we can say, well, then don't try slopes at slope, because that'll return an error. Just return, in that case, just give us 0 instead. But here we'd want 1, and then we'd say plus 1. So this is like kind of a way to count up stuff. So we're saying if there isn't already this slope in slopes, then initialize it with 1 and then immediately add 1, so it'll be 2. So either add slope to slopes with a value of 2, or if it's already in there, just add 1 to it. Whoops. Oh, I deleted the extra line. So this is very slightly faster in theory. But again, I mean, we're at the point where just the random server-side stuff is certainly accounting for all of it. Another thing we could do that theoretically would make it faster, but does seem to unequivocally make it slower, is to prevent ourselves from recalculating the same line over and over again. Like in this situation here, let's say we're looking at this point and then that one and then that one and then that one. If we're looking at this point and then we're saying, oh, these 3, so we have a line of 4. Okay, great. That's our answer already. If we look at this point, we're already optimized to the point that we're never going to look back at this point, but we're still going to compare this point and this point, which we don't want to do because this point's already been compared with this point at a previous point. So what we can do is use another dictionary to keep track of that. So we'll say something like scene equals default dict using a set. So what this is going to do is saying the default value for every key is just a default set. And then we'll say, okay, after we calculate the slope, if we've already seen this slope, if slope in scene at I, continue. oops. And then we also want to add it. So in the case where we haven't seen it yet, we want to say scene at j dot add slope. So then, for example, in this first one, and that actually is probably worth doing. Let's say right here, print points at I, points at j. So here, without this optimization, let's actually see that. So without this optimization, what's going to happen is it's going to say, okay, look at point 1 and look at points 2, 2. Sorry, look at point 1, 1, look at point 2, 2. And then look at point 1, 1, and look at point 3, 3. And then it's going to say look at point 2, 2, and look at point 3, 3. But we actually don't need that comparison because we already have established that those two are on the same line. So if we add this continue in, we say, actually, we've already seen point 2, 2 at this slope. Then we see that it's not comparing those anymore. So if we run this, it actually is probably going to be slightly slower. But what are you going to do? And then the final thing to do is to consolidate all of this into like one-liners, essentially. And it's more elegant, but it's also faster. And a good rule of thumb, specifically in Python, is that every line of code you're writing is a lot slower than if you used a module. Python is just a slow language, but when you're using things, let's say you're importing TensorFlow and you're using that, it doesn't matter if you're using TensorFlow in Python or if you're using TensorFlow in C++. It's all already optimized under the hood. So for example, this for I in range n, for j in range I plus 1 and n, we have two nested loops. And Python is stepping through very slowly to do all of this because Python it's a pretty high level language. But if we consolidated these somehow, if we used enumerate or something like that, then that would be faster. So a quick way to do that would be something like, we'll say for I and x1, y1 in enumerate points. And what we're going to do is we're going to count through all the points, and then we're going to look at all the points past that. I mean, we're just rebuilding the same algorithm. So really here, we wouldn't want to look at the last point. So let's say something like that, which means go from 0 is the default here. And then the colon means, okay, now go until -1, so the last index. So basically do everything except the last one. And then I want to use a counter is the big idea here, because earlier we were counting up. Whenever you have like a dictionary.get a value, comma 0 or a value, comma something, and you're kind of counting up, you can use a counter for that. So we know that here we're going to have something like this. And we'll call this slopes. And what this is going to represent is all, or I'll call it lines even, all the lines going through point I. And this will look something like, we'll have this, we'll say y1 minus y2 over x1 minus x2 for x2, y2 in points at, and then we want to say I plus 1 to the end. So we look at every point past I. So here we would look at these two, and then count them as x2 and y2 and so on, calculate the slope. But the other thing we need to count for is this vertical sloping. So we say something like here, okay, it's this if x1 doesn't equal x2, else we'll just say infinite or none maybe, if we're really trying to optimize. Because it doesn't matter, it's just going to be used as a key. So then this counter is like, we don't really care about this being a number. It's going to say the counter at none is the number of points on the vertical line is what that's going to represent. And then we'll just say ands equals max ands and maximum of lines. And then here we need to initialize ands to be 1 again. Oh, oops, we want this to be max lines dot values. Oops. Okay, we'll say lines. I know I'm missing something very basic here. There we go. Okay. Except this is going to be +1 because here we're counting up the number of other points, but we're not including the point I. So here we would say ands and max of that +1. Cool. So now we run it, and I guess that's about as fast as you can possibly get. We're not performing the optimization that we performed here. We're not using the scene dictionary, but again, I guess the test cases don't really account for that. So that's the solution.